course, many more complicated solutions are possible for a wave equation like this one. And those can show many different examples of this idea of wave interference. One useful conceptual way to think about some of these ideas is the idea of what we call diffraction. Diffraction is the name we give to a variety of wave interference effects that we can see as a wave propagates. For example, waves tend to spread out as they propagate, giving what we call a diffraction angle. In thinking about waves in the late 1600s, Christian Huygens came up with the idea of what is called Huygens' principle. He was trying to understand how waves propagate and how to think about that. And he proposed that we could see what would happen next with a wave as it propagated forwards if we pretended that at every point on a wavefront, some sort of wave peak here, that at every point on there were point sources radiating cylindrical waves, if we were talking about 2 dimensions and water waves, or spherical waves in 3 dimensions. And he realized that adding up the net waves from all these imaginary sources that he put on the wavefront would actually allow us to calculate the next wavefront, and so on. Now, this principle is not quite exactly correct mathematically when stated precisely this way, but the basic idea is a very good one. And with some refinements, it can give us quite a good model for diffractive effects. Basically, if we know what one wavefront is now, we can calculate what its propagation will be like. Models that do that based on calculating the propagation from what we know about the wave now are called diffraction models. We can illustrate this idea and show some of the diffractive effects by looking at the waves from point sources.
So let's think about a wave from a point source. Here's a snapshot of the wave that we would get from a point source. Point source is here, and we're generating these circular waves. And we're getting this snapshot of the kind of circular expanding waves we would get as a result. And we can watch this wave propagate. We can see that it generates circular waves propagating out from this source here, circularly expanding wave. Suppose then that we wanted to know the answer to the following problem. We've got some wall here, and there's an aperture or a hole in the wall, and we're shining plane waves at this wall from the left. What do we get out here, and how can we understand that in terms of diffraction theory? Well, we can appeal to our Huygens principle and try to construct Huygens sources along this line that we've drawn here that attempt to project what is going to happen out to the right. And because this is a plane wave here, these Huygens sources would all be the same amplitude, and we would just put them along this line here and try to construct what would happen out on the right-hand side. Well, as I said, we could put our Huygens sources in here in our gap in the wall to try to calculate what is going to happen going forward. And we could start by just using 3 of these point sources to try to describe the transmitted wave. Now that doesn't really look enough and isn't enough, and let's see what happens here. So this is what the wave would look like from just 3 point sources here. The result really is not very accurate. We're not getting what would actually be the real propagation through this aperture yet. If we use 5 point sources, however, things start to look a little better. In fact, we see if we look out here that we're actually beginning to see kind of plane phase fronts, which is what we might think would happen with plane waves that were on the left trying to propagate through this aperture. So let's look at that evolve. It doesn't look terribly accurate in near to the aperture itself, but out here in the far field, it's getting quite good. With 9 point sources, we can see we're getting something that looks more like what we wanted. Progressively, these are really beginning to look like kind of plane waves that have propagated through the aperture. And we can also see that these circles here, which we drew as examples of phase fronts from each of those sources, are really beginning to form a pretty good straight line along here. And that straight line does indeed essentially follow the kind of phase fronts we're getting. So we're beginning to see Huygens' principle working. And here's the line that we're beginning to see emerging there. And as I said, they generate nice plane phase fronts as we get further out, as if the instant wave had propagated through the aperture. And if we go up to 17-point sources, we see these Huygens sources really beginning to do their job. They're nicely generating a sort of line here as the asymptote to all of these circles. We're getting relatively nice plane waves out here further away from the Huygens sources. So it looks like these Huygens sources are doing their job. They're giving us essentially a plane wave going through this aperture here, which is what we were looking for. And there's no point in putting in more sources here, at least on the level of the graphics that we have. It doesn't make any more difference. So we've essentially converged in a good description in this model. And we're obtaining our initially plane wave fronts, at least here, as if the wave was propagating through the aperture. Now, we do also see that something is happening on the right. The waves seem to be getting weaker out here. In fact, what's really going on is they're actually spreading out. And we'll see just what's happening here if we take a view zoomed further back from all of this.
So as we move far from an aperture like this, the waves spread out progressively. Relatively far from the aperture, they settle into a simple and uniform expansion. An expansion with a characteristic angle called the diffraction angle. We're going to look at that. How we define that angle precisely depends on the very specific shape of the original beam or source. But regardless of that slight uncertainty, it has some universal characteristics. And we're going to see similar behavior later on in quantum mechanics, where it has some important and very basic implications.
So here's what happens if we look far away from a set of sources like that. Now I've just drawn a little set of sources here, as it were. This orange line is really representing that. And I've chosen a set of sources that cover a distance of 2 wavelengths vertically here. When we look far away, what we see is this expansion going on of the beam. So explicitly, for a source or aperture of width d, whatever that is, the diffraction angle, which is this effective diffraction angle, this spreading angle here, is of the order of the wavelength over the aperture size. Now, this is deliberately a bit approximate because what you call the diffraction angle is partly a matter of taste. Do you choose it as this point, or do you choose it as this point, or some other point here? But no matter which point you choose, you still get the same basic result, that the diffraction angle is proportional to the wavelength and inversely proportional to the size of the aperture or the source. Lambda is our wavelength. And note that if we make a larger aperture here, now we've gone up to 4 lambda, the diffraction angle has become smaller. So a larger aperture gives a smaller diffraction angle. And similarly, a smaller aperture, now we've reduced the size of the aperture or source to just 1 wavelength, gives a larger angle. This is a very general phenomenon with waves, and you see it all over the place. You're quite used to it in the behavior of loudspeakers, where the high-frequency loudspeakers are quite directional, but the low-frequency loudspeakers are really not very directional.